half a century since conferring the name Songkla Nakarin, it has served as a compass, guiding the way for Prince of Songkla University, creating every mission with the benefit of mankind as a priority. In a land full of valuable and diverse cultures, from the roots of traditional knowledge combined with modern education and science systems, presenting opportunities and raising the level of equality for development in all sectors. By establishing an education system that emphasizes the multicultural exchange of diversity and a mutual understanding for harmonious coexistence in society. Prince of Songkla University focuses on teaching and learning that emphasizes the development of knowledge and skills that will be useful for future careers, through faculty with expertise in various fields of study, focusing on the use of modern technology in teaching and learning management. Thus, students can master a variety of skills and apply their knowledge to solve practical problems, covering all fields of study. Prince of Songkla University creates a society of knowledge by providing appropriate environments for conducting research through Research and Innovation Center in variety of fields such as health science, science and technology, and humanities and social sciences, all with the goal of fostering efficient innovation and technology, ready to develop a value society, driving efforts towards becoming a world-leading research university. Prince of Songkla University plays an important role as a source of knowledge, providing academic services that cover the needs of all sectors, responding to social and economic development by coordinating with partners from the public and private sector, through innovation and technologies that are beneficial to development, while also strengthening competitiveness at regional and international levels. Prince of Songkla University places utmost importance on preserving and inheriting arts and culture by utilizing local wisdom, fostering understanding and pride in valuable local cultures, and strengthening the indigenous identity with readiness to expand and disseminate this valuable knowledge to the international community. Recognizing the outstanding potential of all areas, Prince of Songkla University reflects an atmosphere suitable for learning and self-improvement, cooperating for the benefit of mankind as one in the midst of a volatile world. Guided by leadership that aims to achieve the same goal, which is to create personal innovation to develop the southern region and the country, and convey a trustworthy academic quality at the international level. Prince of Songkla University continues its unending task of moving forward and continuing to grow alongside humanity, aiming to be a valuable university. Prince of Songkla University.
Very good afternoon to our distinguished guests. Ladies and gentlemen, my name is Dr. Suriratchana, a lecturer in physics, and I will be your Master of Ceremony today. On behalf of the Faculty of Science, Prince of Songkla University, it is our great honor to welcome you all to attend this very special event. To celebrate its 55th anniversary, Prince of Songkla University is hosting a series of exclusive lectures by 5 Nobel laureates in economics, physics, chemistry, and medicine here at the Hat Yai campus, in close collaboration with the International Peace Foundation, or IPF. The special lectures are also part of the Japan-ASEAN Bridges event series to celebrate the 50th anniversary of Japan-ASEAN relations, facilitated by IPF and sponsored by Mitsui Fudosan Group, Dusit Hotels and Resorts, Kasikorn Bank Public Company Limited, BMW Thailand Company Limited, and the Japan-ASEAN Bridges. As just shown in the introductory video, the 5 lectures take place from November 2023 to March 2024 and are organized by the Faculty of Medical Technology, Faculty of Science, Faculty of Pharmaceutical Sciences, Faculty of Economics, and Faculty of Medicine. Today, the Faculty of Science welcomes you all to one of the 5 lectures in the series. Without further ado, I would like to invite Professor Anchana Pratep, the Dean of the Faculty of Science, Prince of Songkla University, to deliver a welcoming remark.
Good afternoon, everyone. Esteemed President Assistant Professor Dr. Niwat Kewada, Honorable Professor Takaaki Kajita, Nobel Laureate for Physics, Mr. Uwe Morawetz, Founding Chairman of the International Peace Foundation, distinguished guests, ladies and gentlemen. Welcome to this second talk of Japan-ASEAN Bridge events, silly here at PSU, co-hosted by us, the Faculty of Science. We are celebrating 2 milestones today. 55 years ago, the Faculty of Science has been one of the founding faculty of PSU. And 19 years ago, our faculty had the privilege to host a bridge event also in collaboration with the Peace Foundation. Back then, we could not have imagined how proud we stand on the world stage once again to co-host this Nobel Laureate talk, this time on the importance of science for peace building by Professor Takaaki Kajita, Nobel Laureate. It is indeed a fitting model given the long-established track record of PSU as a factor of peace and development in relative South. Our academic endeavor toward peace and scientific progress has transformed the region and brought together people of vastly different backgrounds for a common cause. Recently, as a Faculty of Science, we have been expanding this endeavor to the international community. And indeed, we have our case to become one of the best in Asia and to put forward ourselves for a better science and a better society. I am certain that our perseverance added by the insight of the esteemed Nobel Laureate will inspire our faculty, staff, students to reach our goal to play a valuable role in the international scientific community. Again, it is a privilege for us, the Faculty of Science, to co-host a talk of these Japan-ASEAN Bridges event series here at PSU. And I'm grateful for everyone to make this opportunity happen. As we come to the conclusion, I'm honored to invite PSU President, Assistant Professor Dr. Niwat Kewada to kindly deliver the opening remark. Thank you. ขอบคุณค่ะ
Good afternoon, everyone. Honorable Professor Takaaki Kajita, Nobel Laureate for Physics, Professor Archana Pratep, Dean of Faculty of Science, Prince of Songkla University, esteemed Mr. Uwe Morawetz, founding chairman of the International Peace Foundation, distinguished guests, students, ladies and gentlemen. On behalf of Prince of Songkla University, it is my great pleasure to join the second event under the Japan-ASEAN Bridges event series at PSU today. On the occasion of Prince of Songkla University's 55th anniversary, we are grateful to be able to host 5 auspicious events under this series in collaboration with the International Peace Foundation. I'm proud to note that Prince of Songkla University has been leading in terms of innovation, research, and higher education, both in the southern region and nationwide. A large part of this success is due to our excellent Faculty of Science, Prince of Songkla University, which has been an integral part of PSU since its foundation 55 years ago. This is why I am confident that today's event, co-hosted by the Faculty of Science, will both increase our institution's global visibility, research networking, and reputation, and serve as significant milestone towards the betterment of society. I strongly believe that the insights we will gain from today's talk, entitled "The Importance of Science for Peace Building," delivered by Honorable Professor Takaaki Kajita, will inspire our faculty members, students, and all participants towards achieving greater goals and elevating our community to greater heights. I would like to extend our special appreciation to Professor Takaaki Kajita, Nobel Laureate in Physics, for sharing his inspirational wisdom with us today. I would like also to express our gratitude once again to the PSU Faculty of Science for co-hosting this auspicious event, and of course to the International Peace Foundation for starting PSU to make the event happen. Finally, I wish to convey my sincere wishes that this talk would become a successful event, able to inspire the youth of Southern Thailand. Hope everyone will enjoy and be inspired by today's talk. Thank you very much.
Next, I would like to invite Mr. Uwe Morawetz, founding chairman of the International Peace Foundation, to deliver an introductory remark.
Sawadee Krap, and welcome to the Japan-ASEAN Bridges event series facilitated by the International Peace Foundation. The events are hosted in cooperation with various local partners, including some of the country's major universities. And I would like to thank Prince of Songkla University for hosting our event today. Commemorating the 50th anniversary of official relations between Japan and the ASEAN region, bridges will be continuously held in Thailand and Japan until March, involving the participation of Nobel laureates for physics, chemistry, medicine, and economics. The Japan-ASEAN Bridges series follows the series of over 800 bridges events, which the International Peace Foundation has facilitated since the year 2003 to support education in the ASEAN region. Bridges has been established as an international, intercultural, and interdisciplinary platform for creative cultures of learning and continued education for all people. The International Peace Foundation has no concept for peace and no fixed solution how to achieve peace, but we believe that the first step towards peace is dialogue, and the first step towards dialogue is respect. The International Peace Foundation does not take sides, but acts as a mediator by creating an independent platform for dialogue where people can meet who normally don't meet. People from all walks of life who speak different languages, even if they speak the same. As politicians speak another language than artists and business and religious leaders, another one than scientists, it is seldom that they speak with each other or even work together. We live in a world where some people pretend to know the answers and solutions, how to fix problems, how to achieve peace, though the quest for peace lies in the art to pose the right questions. The International Peace Foundation believes that the interconnected problems of our world today cannot be solved only by politicians, only by business, only by scientists, or by religion alone, but by working together. In the Bridges event series, people from all walks of life meet in a multidisciplinary program to find creative solutions to solve problems and to achieve peace. Peace within ourselves, peace within our families, our social structures, peace with nature and the environment, peace between nations, cultures, and religions. Peace is a process. Dialogue is a process. It is nothing which can be achieved instantly. It needs time. This is why Bridges is not organized as a single conference, but as a series of events of now over 2 decades, in which Nobel laureates have built bridges with leaders in all parts of society and with the general public. Peace is not something which can be left to the elite of a few, but which needs the participation of everyone. Only if many ways cross and people walking these ways meet, can international understanding be achieved and problems commonly solved. If we listen to and learn from each other, we may discover that there is not only one way to achieve peace, but that there are many ways, and certainly ways we have never thought of to go. It is my pleasure to invite you today to listen to and to share your views with Professor Takaaki Kajita, a Nobel laureate for physics who has agreed to come to Thailand to help build bridges. We all look forward to his keynote speech and to his important contribution towards peace. A warm welcome, Professor Kajita. ขอบคุณครับ
Once again, please join me to give a very warm welcome to Professor Takaaki Kajita.
Okay, well, good afternoon. Well, first of all, thank you very much for the kind introduction. And I want to say it is really a great pleasure for me to give this talk in the occasion of the 55th anniversary of the Prince of Songkla University. Congratulations. So today I'm talking about the importance of science for peace building based on my scientific experience on neutrinos and gravitational waves. This talk is one of the series of the Japan-ASEAN Bridges event series. So I want to discuss again the importance of science for peace building. Okay, this is the outline of this talk. First, I want to briefly introduce my research history. Then I want to discuss neutrino research, gravitational wave research, and I want to summarize this talk. Well, okay, first, I want to tell you my research history. I became the graduate course student in 1981, and I joined the Kamiokande experiment. That was famous for the neutrino research. Then we moved on the Super Kamiokande experiment. This is the current neutrino experiment. And I worked on this experiment for many years. But around 2010, I decided to move my research topic from neutrinos to gravitational waves. And after that, I have been working on the Kagura project. Now, I mentioned Super Kamiokande and Kagura, and you may not know the location of these experiments. So I want to tell you, the location of these experiments are shown there in the Japan's map. First of all, you notice that the indicated location is not a flat place. Indeed, it is in the mountain area. And in fact, Super Kamiokande and Kagura detectors are located deep underground. Well, of course, we have reasons to locate these detectors in deep underground. Super Kamiokande is a neutrino detector. We are going to measure rare events. And in order to measure rare neutrino events, we have to reduce the backgrounds. They are cosmic rays, and therefore, if the detector is located at the surface, then our data would be really dominated by background. Therefore, we go deep underground. Also, Kagura is located deep underground. Well, Kagura is going to measure a very small effect of gravitational wave. And if the detector is located at surface, then the seismic activity at the surface is too large. So we decided to locate this interferometer in underground. By the way, I came Thailand about a week ago, and since then, I'm very happy with the warm weather. Well, certainly the location of our experiments are a little bit different in weather. For example, in winter, our experiments are located in this area. And in fact, for example, if you want to go to Super Kamiokande, you come from this tunnel, and of course you can see snow. So this is our experiment. By the way, of course, this has nothing to do with my talk, so let's move on. Okay, now I want to discuss neutrinos. Well, I think some of you may not know much about neutrinos. Therefore, I want to have a brief introduction on neutrinos. Well, I'm sorry for boring slides, but anyway, let me tell you, neutrinos are fundamental particles like electrons and quarks. But maybe still you do not have no idea what are neutrinos. Then I want to tell you that neutrinos are something like electrons, but without electric charge. Well, in fact, this is, to me, this is in fact a very good answer on neutrinos. And in fact, because of this nature, electrons without electric charge, they can easily pass through even the Earth. But they can interact with matter very rarely. Therefore, we study these neutrinos when these neutrinos interact with matter very rarely. So these experiments are not easy. And neutrinos have three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to say that neutrinos have been assumed to have no mass. Okay, but well, of course, you still do not understand how we measure these neutrinos. Well, okay, let me tell you. Well, first of all, we can never see neutrinos themselves. However, sometimes neutrinos could interact with their nucleus. And then, in this case, charged particle is emitted. And in fact, we have various ways to observe these charged particles. For example, if this nucleus is a water nucleus, then this charged particle propagates in the water, then photons or light are emitted. Of course, if the light is emitted, we have various ways to observe these photons or light. So we use photodetectors to observe these light. So these are the data. Then by analyzing these data, we understand the neutrino interactions. So this way, we study neutrinos. Okay, I would like to move on to the experiment, Super Kamiokande. Well, Super Kamiokande is a very large neutrino detector. It is about 40 meters in diameter and 40 meters in height, containing 50,000 tons of very clean water. And you see a photo of the Super Kamiokande. This photo was taken when we constructed the Super Kamiokande detector in 1996. So since then, we have been studying neutrinos. Now, let me tell you our collaboration history. First, we had an extensive discussion with our US colleagues at our Institute for Cosmic Ray Research in 1992. So this was the photo we took after a very intense meeting. And finally, we agreed to work for the Super Kamiokande experiment. Of course, this was not an easy discussion, but well, the meeting went well. As you see, many beer bottles on the table. Okay, anyway, after this discussion, we worked together between United States and Japan, and we have about 100 collaborators at that time. Then, well, the construction continued, and in 1995, the underground cavity was excavated, and the tank was constructed. Then, physicists came to underground to construct the detector itself. So this photo was taken in the spring of 1995. So we worked together in underground for about a year to construct the Super Kamiokande detector. And in fact, I think this kind of intense work was really important to understand each other, US and Japan, who have different cultural and historical background. So really, we became the collaboration after this intense work. Anyway, the construction went well, and the experiment started in April '96. And since then, we have been studying neutrinos. Well, there are several neutrino sources that Super Kamiokande studies, and one of them is the neutrinos produced in the atmosphere of the Earth. Well, let me explain briefly how the neutrinos are created in the atmosphere. Well, there are high-energy particles in the universe called cosmic rays. These are high-energy, say, protons, mostly, sometimes high-energy helium nuclei, or sometimes even iron nuclei come to the Earth. And if these cosmic ray particles come into the atmosphere of the Earth, they interact with the air nucleus, and typically after this interaction, pions are produced. But pions are unstable, decay to other particles, and during these decays, neutrinos are created. And these neutrinos, well, most of them simply pass through the Earth. But some of them interact in the Super Kamiokande detector. And if they interact in the Super Kamiokande detector, the data taken in the Super Kamiokande detector look like this. So this is one example of the neutrino event observed in Super Kamiokande. So you see a ring shape. This is a typical pattern of the neutrino event. And Super Kamiokande observes about 10 neutrino events in a day. And, well, this looks simple, but there are, of course, many backgrounds and so on. Therefore, many collaborators from the US and Japan worked together to study these neutrino events. Now, what do you want to know with these neutrinos? Well, one thing we wanted to know from the beginning was we wanted to know if neutrinos oscillate, neutrinos or neutrino oscillations. If neutrinos have mass, neutrinos change their their type from one type to the other. For example, if a muon neutrino is created at the left corner and begin to propagate to the right, then at some point, the neutrino type could change to tau neutrino. But this neutrino still continue to propagate, then come back to muon neutrino, then tau neutrino, and so on. So this is neutrino oscillations, and this was theoretically predicted more than 50 years ago. And we wanted to know if neutrino oscillate. Then, of course, we carefully studied the neutrino data, and we come up with this kind of plot. I'm sorry, talking about science too much, but anyway, let me allow to show you just this single graph. So this graph shows the number of neutrino events observed as a function of the neutrino arrival direction. Horizontal axis is the neutrino arrival direction. 1 means downgoing neutrinos. They are produced in the upper atmosphere. -1 means upward-going neutrinos. They come from the other side of the Earth. So they have to propagate a very, very long distance before reaching to the Super Kamiokande detector. Now, the vertical axis is the number of neutrino events observed, and the data are shown by black circles with the error bars, and the expectation is shown by the shaded histogram. Then you find for downgoing neutrinos, the data and simulation agreed well, but for upward-going neutrinos, data showed almost a factor of 2 deficit compared with the simulation. And in fact, this is exactly expected for neutrino oscillations. If neutrinos propagate for a long distance, they change their type. Therefore, neutrinos from the other side of the Earth, when they arrived at the Super Kamiokande detector, the probability that muon neutrino remain as muon neutrino is essentially 50%. So this way, we discovered neutrino oscillations in 1998. Well, certainly, the whole Super Kamiokande collaboration was really excited. But I want to tell you, the excitement was not only us, but there was a mention by the US President, President Clinton, in his talk. He gave a talk at the MIT's 98 commencement. And well, the whole talk was, I think, about 30 minutes. But at the middle of his talk, he mentioned the discovery of neutrino oscillations. Let me read what he said. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Well, certainly it was really great to hear this kind of words from the US president on the next day of our announcement of the discovery. Of course, as the US president, he mentioned that in Super Kamiokande, physicists from the US is working, collaborating. Then he came back and continued, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, indeed, it was really an honor for us to hear this kind of words from the US president. And indeed, we think scientific collaboration is really very important, well, as I discussed later, for the peace building. Well, about a year after the discovery announcement, we had a news that Super Kamiokande collaboration will be awarded the Asahi Prize. This is a very prestigious prize in Japan. And this photo was taken at the time at the top of the Super Kamiokande detector. So, you see, we were really very happy. We really felt that we worked as a team. Now, after this discovery announcement, the whole neutrino community realized the importance of neutrino physics. And because of the success of the Super Kamiokande and the importance of the neutrino physics, many more people joined Super Kamiokande recently. Well, initially, Super Kamiokande started as the US-Japan collaboration with about 100 people. Now, we have about 230 people from 11 countries. Well, but I think it is really important to work together to really become a collaboration. And in fact, in 2018, there was a large-scale detector improvement work, and these 230 collaborators come to the site and worked together. So I think this was really a great opportunity for us to really understand each other and to become a real collaboration. Again, we think the collaboration, international collaboration, is very important for science. Now, well, certainly it was very nice to hear from President Clinton, but maybe you ask why he was so excited Well, of course, electrons have mass, quarks have mass. Then, in a sense, it's natural that neutrinos have mass. Why they are so excited? Well, let me tell you why we are excited. Here, I show the mass of charged leptons, electrons, muons, tau, and the mass of quarks. They are shown by red, green, and blue colors. Well, we found that neutrinos have finite mass. And since then, the world community have really worked hard to understand the neutrino mass itself. And now, we think we understand the neutrino mass reasonably well. And the mass could be like this. But unfortunately, we do not know the lightest neutrino mass. But for the second and third neutrino mass, we understand pretty well. Now, looking at this figure, you find the neutrino mass is plotted in a rather different place on this figure. And please be careful about the horizontal axis. 1 unit is 100. So this tells us that the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude smaller. Very, very small. And we believe this is the key. This smallness is the key to better understand elementary particles and the universe. Therefore, we are excited. Of course, if we understand why neutrino mass are so small, we understand better elementary particles, but the universe could be related. Why? Well, let me tell you why we are thinking that neutrinos could be important for the understanding of the universe. Well, this is a photo taken by the Subaru telescope in Hawaii. You find many galaxies. And these galaxies are made of matter particles. We know that there's no antimatter galaxy. Well, of course, this is obvious. We know this fact. But if you think about the history of the universe, this is non-trivial. Well, we believe that about 13.8 billion years ago, the universe was born. And at the beginning, the universe was extremely hot. And in this extremely hot universe, particles and antiparticles were always created simultaneously. And therefore, in the very hot universe, the number of particles and antiparticles should have been equal. Then, with the universe cooled down, particles and antiparticles meet and annihilate, disappear. Then, of course, you can easily imagine, at present, there should be no particles, no antiparticles. But we exist. So, there must be something wrong. There must be something we do not understand yet. And in fact, we do not understand what happened. But there's an interesting idea that neutrinos with very small mass might be the key to understand this big mystery of the matter in the universe. So we think neutrinos could be very important, and we think we have to continue study these neutrinos. And therefore, at present, the next generation neutrino experiment is under construction. I do not want to go into details, but this new experiment is going to be a very large experiment. And well, you can see this photo. And if you look at the photo carefully, there are many people there. So this is going to be a very large neutrino detector. And well, people are really excited with the science of neutrinos. And therefore, in this project, about 600 members from 22 countries come together to work together in this project. Now, let me talk about the collaboration of this next generation experiment. This is truly an international collaboration. We have collaborators from 22 countries. And well, this is actually a slightly old view graph, but you may notice there are collaborators from Ukraine and Russia. So people are really wishing to work together in this scientific project. And we really hope that the peaceful world will be restored as soon as possible. Now, well, maybe I'm spending too much time, but let me move on. Gravitational waves. I want to move on to the gravitational waves. Well, more than 100 years ago, Albert Einstein predicted gravitational waves based on his theory of general relativity. General relativity is a theory of gravity. Now, let me show you this movie. This is a simulation of the merger of two black holes. There are two black dots that they are black holes, and they are orbiting each other and emitting gravitational waves. Therefore, by emitting gravitational waves, they come closer and closer and orbit faster and faster. Then come closer, closer, closer. Yeah, okay. Now, motion gets too fast, therefore the movie slows down. Then finally, two black holes merged. After the merger, still heavier black hole remained. And if you look at the outer space, you find that gravitational waves are propagating to the outer space. So we expect this kind of effect should be observed, or should be happening, therefore we should observe this effect. And in fact, in a very short word, gravitational wave changes the length of the space. Therefore, we'd like to observe the length change due to gravitational wave. Then the question is how we observe, and indeed, we use laser interferometers. And here is a laser, and here is a beam splitter. Half of the beam goes straight to this mirror, and half of the beam is reflected to this mirror. Then the light are reflected to these mirrors, come back here, and there's an interference, and the interference is observed in this mirror. Let me show you. Okay, So this is the image of laser light. The laser light is reflected at the far mirror. Then they come back and there's an interference. And typically the detector is tuned so that the interference rate is minimum here. However, by some reason, if the mirror position changes, then the interference pattern changes. And for example, if this is due to gravitational wave, we should be able to observe this pattern. So this is the signal we want to observe. Now, you may ask, what kind of science do you have with these observations? Well, in fact, at this moment, our main targets are these two. One is the merger of binary black holes, the other is the merger of binary neutron stars. And, well, first of all, well, maybe I do not have time, therefore I only mention this. Well, neutron stars are, say, heavy star. Their mass is about 1.4 times the mass of the sun, but the diameter is only 25 kilometers or so. Very heavy, very compact. But now we think the merger of these binary neutron stars plays a very important role in the universe. For example, they could be the origin of heavy metals in the universe. That means, well, we have gold, silver, but we do not know yet where these heavy metals were generated in the history of the universe. So, by the observation of this merger of binary neutron stars, we do have to understand the origin of these heavy metals. Anyway, already gravitational waves were observed about 8 years ago. This was the discovery of the gravitational wave. The signals came from two laser interferometers in the United States. And in fact, the two data from these interferometers agreed very well. And from this, we were convinced that gravitational waves exist. And in fact, at that moment, we think the gravitational wave astronomy was born. Then after that, the observations are continuing. And this is a summary of the gravitational wave events observed so far. And so far, 90 events were observed. Most of them are merger of the binary black holes, but there are some binary neutron star mergers or neutron star black hole mergers. And certainly with these observations, we'd like to understand the universe better. And therefore, this field is quite new and quite exciting. And therefore, we'd like to contribute to this field. And we have the Kagura project. And in the remaining time, I want to discuss briefly about the Kagura project. Kagura is, again, an international collaboration. We have about 150 authors of papers. They come from 8 countries and regions. And these 8 countries and regions are listed here. And you find that main contributors are from Asian countries. China, Hong Kong, Japan, South Korea, Taiwan. Then you find a very important missing country, So we'd like to collaborate with the scientists in Taiwan. You are very much welcome to join us. Anyway, let me talk about our project a little bit more. Well, as I said, Kagura is located underground. We have 3 kilometer by 3 kilometer arm for the laser interferometer. And this is located in underground to minimize seismic noises. And in addition, we use cryogenic mirrors to have better noise control. And I want to briefly show you the construction of the Kagura interferometer. Well, first, we have the 3 kilometer vacuum tube for the laser light. In fact, this is a rather big vacuum tube. Diameter is 80 centimeters. And this is the central area. Well, you cannot see very well, but there are many vacuum tanks. And in each vacuum tank, typically we have one big mirror suspended by the seismic isolation system. And finally, you find one example of the mirror. This is a mirror to be cooled down to 20 Kelvin. And in fact, this is a rather expensive mirror because this is sapphire, 23 kilogram sapphire. Of course, this is a man-made sapphire, but anyway. So, anyway, for about 10 years, we worked for the construction of the laser interferometer. Then in 2019, we finished our first construction period. Then the next thing is to operate the laser interferometer. And the control room for the laser interferometer is located at the surface. And this is the photo of the control room. And well, I want to say at this stage, only young people can contribute to the project. Old people are, well, are not doing well, cannot do well at this stage, unfortunately. Anyway, still, of course, even old people are collaborating. As I said, Kagura is an international collaboration based largely on Asian countries and regions. And we work together for the Kagura project and for the gravitational wave astronomy. And this photo was taken in August 2019, before the COVID-19 pandemic. And since then, it was not possible to have this kind of gathering. But, well, certainly, COVID-19 suggested us strongly the importance of meeting or working face-to-face. It is really important to work face-to-face to really collaborate. So we are very happy now COVID-19 pandemic period is essentially over. So we really work hard for the Kagura project together. Now, I discussed that Kagura project is mainly an Asian international collaboration. But you may ask why. Well, there's a reason. This is the map of the laser interferometers detecting gravitational waves. Now, there are LIGO interferometers in US, Virgo in Europe, and we have Kagura. And so, therefore, Kagura is mostly an Asian international collaboration. But at the same time, it is very important to realize that the scientific output will be maximized by the global network by combining all these data together. For example, the pointing accuracy of the gravitational wave event will be much improved by combined analysis of all the gravitational wave data. Therefore, Kagura joined the network observation with LIGO and Virgo. That means we are working together globally. Asian, European, and US projects are working together. Okay, so far I discussed the Kagura project. Now, before finishing, I want to mention the one announcement made by the International Union of Pure and Applied Physics. Well, so far I discussed the importance of international collaboration, scientific collaboration. But I would like to convince you that this view is shared by the international physics community. Let me tell you, this is the statement of the International Union of Pure and Applied Physics, IUPAP. This statement was issued on March 1st, 2022. A few days after the Russian invasion to Ukraine. And of course, we were very much worried about this. But, well, for today, I want to focus on the later part of this statement. Let me read. In our 100th anniversary this year, we note the critically important historical role that IUPAP has always strived to play in bringing physicists together across political divides, even during our most difficult years in the past. IUPAP continues to embrace and promote scientific collaboration across the world as a driver for peace. So this is the view of physicists, and I believe this is also shared by many other scientists. So we really think that the international collaboration is important for peace building. Okay, let me summarize. Neutrinos and gravitational waves are exciting scientific fields. However, to promote scientific results, to produce significant results, we need large and complex detectors. To construct and operate these detectors and to analyze the data from these detectors, we have been forming large international collaborations. And of course, we work together for science. And in my view, science is more important than the political device. I think that science, in particular, international scientific collaborations, plays extremely important role for peace building. And finally, since there are many young people here in this room, I want to say that I hope that many of you become scientists to contribute to the scientific development and to the peace building. And I also hope that Thai and Japanese scientists work together much closely in scientific collaborations. Okay, that's all. Thank you very much for your attention.
Thank you very much, Professor Kajita, for the very inspiring talk. Now it's time for the questions and answers session. For the audiences who want to ask a question, please, you can raise your hand and we will pass you the microphone. And could you please introduce yourself in short before asking the question? And I may ask you, you may have like 10 questions in your mind, but please ask one by one. So Professor Kajita can answer one by one. So can I get the first question, please?
Uh, I have heard from you that the project that contributed by several countries can create harmony and can stop the war, but it have another consequences as well when something that dangerous or can be used to military purpose. It happen quite often. So everyone got the inside information about that dangerous scientific knowledge, right? And it can cause a very dangerous effect to the world as well. So I wanted to ask you that in the point of view of a great scientist, is it all fault or what do you feel about it? How you want to take responsibility about that?
Well, thank you very much. In fact, that's right. Well, say, looking back more than 70 years ago, there was an atomic bomb, and this was really this had really a very serious effect to, well, of course, to Japan. But, well, certainly atomic bomb was created based on pure science, and physicists played very important role for the development of atomic bomb. Therefore, I think physicists should learn from this experience that we should be explicit to contribute to the peace building. We should not be silent. And on the other hand, we cannot really control the technology development by someone else. But, well, of course, again, we should be explicit to mentioning the importance of the peace.
Thank you. So first, my name is Phongpon Ananaksap. I am a medical student, year 1. So my question is, you know, the first time that I heard about the topic that we're talking about today is the importance of science for peace building, right? But as I say, your presentation is about your work and you work together with a lot of countries. But as many people notice, a lot of innovation, for example, you know, dynamite that the Nobel, the scientific that invent this kind of thing, dynamite can be used for business and also the war. So for me, I don't think that the peace building is about science. I think peace building is something about human. It was human. But so my question is, what do you think about peace building?
Well, okay, thank you very much for this question. Yes, well, of course, our way of contributing to the peace building is not direct, but we think it is really important that people from various countries, from various cultural and political background work together closely. And this way of communication is really important for the peace building. And this is I think this is the way that we scientists contribute to I would say one of the ways for us to contribute to the peace building.
Professor. Thank you very much, Professor, for inspiring talk. And my question relates to the about the gravitational wave research, and mostly you said about a lot of collaboration worldwide, that increasing number of countries joining the project. And as a physicist, I also am also interested in, and it was clear that the physics about data interpretation, modeling, and maybe the theories could be benefits from acquiring data and interpret and make a understanding, right? But how about the other aspect, like developments of the detectors or instrumentation? Because I'm a optical and photonics background, so is there any still room on that aspect as well that need collaboration?
Yes, okay, thank you very much for this question. Well, of course, my answer is yes. In fact, this kind of large interferometer is extremely difficult. And well, I didn't tell you the accuracy we need. We have to measure the length change of 10 to minus 16 meters in 3 kilometers. So this is really difficult. And we need to use all the available technology of optics and mechanics and so on. And so this is really one of the important element of the project. In addition, of course, we need a large number of people who work on data analysis. In addition, we need people who simulate the signal. So all these people have to collaborate in order to get scientific result. So we really need various kind of people to work together in this project.
Thank you. First.
Hello. First of all, I would like to thank you, the Takaaki-san, for sorry.
Thank you.
For doing the work to make the world better. Arigatou gozaimasu. Otsukaresama desu. My name is Sanisuk Shinjun. I'm the PSU student who are studying here. So, so the question that I want to ask you is, if you want to pass on the message to the future generation to inspire the young student or the future generation, to inspire the student to be loved in science, what is the key message that you wanna send to them?
Okay, thank you. Thank you very much. Well, okay, maybe I'm just going to repeat. Well, as scientists, we have to work together with various people in the world. And in fact, this is very important for the peace building, in my opinion. Therefore, I hope many of you become scientists and try to develop the scientific knowledge. But in addition, I hope you contribute to the peace building.
Arigatou gozaimasu.
to turn on the microphone. Then I am Prit Kasawan. I'm a lecturer in physics in this Prince of Songkla University. So my question is about actually I have some experience about, and actually it's kind of difficulty when I try to talk to politicians. I have many opportunity to talk to politicians who have direct responsibility for granting some funding, research funding for the whole country, for the whole country. And I found it very difficult that when we talk to people, for them to pursue them, to tell them, to negotiate them, to support the funding for pure science. And sometimes it's quite a project, like this country want to build the tokamak, for example, like my group, ourselves, we're going to build a quantum computer, quantum technology, the one thing, and they have to spend a lot of money. And it's really difficult to talk to them. And from your experience, you got some advice for me, for us to talk to them, to make them understand how important of this sort of work. That's my question.
So, sorry, I'm afraid I could not catch up your question very well. Sorry.
Oh, okay. So I try to repeat that again. How can you talk to politicians that will support the funding for the research?
Politicians.
Yes, politicians who support the funding to research, to understand how important of the basic science, and they also give us the funding to do the research like that.
Okay, thank you very much. Well, first of all, in the Japanese system, typically, I do not speak to politicians directly because we have the government people who are controlling all these scientific projects. Therefore, essentially, instead of speaking to politicians, we speak to the government people. And well, certainly, it is important that many scientists speak to them the importance of pure science. And well, in my opinion, these people understand the importance of pure science that contribute to the knowledge building of the humanities, whole humanities. So at least I have been doing this way, really telling them the importance of science. Well, in my case, I didn't speak much about the application, potential application of this scientific research. I only spoke the importance of science.
I have a question. Okay, for 3 months ago, I have watched the Christopher Nolan film, Oppenheimer. Whether everyone in this room has watched. And the key message of Oppenheimer is about to warn the honor of the science like a nuclear bomb. And okay, I'm sorry if it is a bad memory of in your country. I'm sorry, but okay, but in this situation we have a war like Israel, Hamas, and Ukraine and Russian wars. And what is your message to the peacemaking and for against the war and notice everyone to know the importance about your research, because your research is about the physics nuclear, right? And what is your message about the against the recent war?
Yeah, thank you for this question. Yeah, well, certainly, unfortunately, we are not the politicians. Therefore, we cannot directly affect the what is happening at present. But as I mentioned, For example, International Union of Pure and Applied Physics immediately issued a statement against the Russian invasion to Ukraine. So I think this kind of work is what we should do. And also in the case of the Middle East at present, I also signed two statements issued by Nobel Laureate. And so this kind of message should be, I believe, received by political people. And I hope our message could have some effect to them.
And I have another question. That how can we do to send a message to not to begin the second nuclear war? Oh, sorry. How can we do to send a message to not to be the beginning of second nuclear war?
A second nuclear.
What is the message that that we can do or we can send to to against the second nuclear war to not begin it again?
Yeah. Well, thank you. Well, this is obvious. This should not happen. So everybody should mention that this should not happen. So I hope many people have big voices against the second nuclear bomb.
Okay, thank you very much.
Yes. Hello. Okay. I'm Takaaki Kajita. I'm medical student. So yes. Okay. Today I'm very happy and I'm very glad to see you. And can you tell me about it? What is your inspiration in your life and your inspiration to succeed in your life? Yes.
What is the
Okay. Can you tell me about what is your inspiration to succeed in your life?
inspiration? What's the success in my
Yes,
life?
of course. Yes.
Well, okay. Well, first of all, certainly, I'm happy with my life because I was able to work on science. And certainly, when I was a child, I wanted to know about the universe, about the smallest particles. And of course, we still do not understand everything, but I'm very happy to try to understand these topics.
Okay, thank you. Give him a big hand.
Okay, hello. Hello, Professor. Can you... Thank you very much for your very interesting talk. In your talk, you mentioned that international collaboration is very important for the science, for the peace building. As a well-known scientist, do you have any recommendations for collaborations between the government and academic institutions to make sure all the scientists are working for the peace building?
Okay, well, Once again.
Yeah, I would like to know, do you have any recommendations for initiatives or collaborations between the government authorities and scientists to make sure we all are working for the science for the peace building?
Oh, okay. Thank you. Well, well, still, I'm not sure if I can answer your question directly. But, well, first of all, science is important, of course. However, at least in our case, in international collaboration is actually kind of recommended for a way of science, and this way we'd like to pursue the international collaboration. And of course, this way we can come to know each other, and this is a good way for the peace building. I'm sorry, I may not be answering to your question.
Thank you very much.
Good afternoon, I'm Professor Kajita. My name is Chitanon Munachai, an associate professor in physics. So my question is really simple. Physics is disliked by many students. Do you have any advice to change their mind on that? Thank you.
Advice to what?
To change their mind, or at least physics is disliked by many students. I mean, they don't like physics at all. And do you have anything to say to that, and anything that can change their mind? Thank you.
Okay, thank you. Well, certainly, forgetting about these difficult things, we would like to understand what's going on in the universe, what's going on in the smallest world. So our question is important. That's what I'm thinking.
Thank you.
First of all, thanks for your talk. It's very inspiring and very informative. My question is, we've seen from your talk already that the large-scale collaboration across many countries can bring people together and promote peace, but it's maybe hard to imagine for us, young scientists and junior research, that how would that begin? Like back in your day,
what?
Back in your day before this kind of collaboration happened, like how would that conversation begin? What happened back then? And in your experience, maybe tell us that story, maybe for us to, suppose we convince them to like physics already, how can they begin collaboration by themselves?
Okay, certainly. Oh, yeah. Well, let me talk about the Kagura case, Kagura experiment. 2010, the Kagura project was funded by the Japanese government. Then we thought it's very important to work together with the international colleagues. And therefore, we started discussion with the people to whom I knew. Then slowly the collaboration get larger. But of course, for example, if a young researcher wanted to join, for example, to the Kagura project, well, of course, he or she should be free to join. Yeah, but of course, because this is going to be a rather large collaboration, it would be nice to have kind of team, a national team or university team to join to the collaboration. And in this case, maybe young researcher needs to convince the old ones.
Thank you.
Okay, sorry, I forgot to introduce myself at first. So, I am physics student and I really love physics. And my name is Korat Pecharat. Yep. I want to ask about the technical to be in my research. So because I have maybe someday I have to do the interferometer like you do in the setup as well. So you said that you stabilize the mirror, the two mirrors in the interferometer. What about the beam splitter, the thing that split the beam in the middle? Why we don't have to stabilize it?
Yeah, have to.
Why we don't have to stabilize the beam splitter in the middle?
Stabilize means isolate from the seismic activities, right?
Yes.
Oh, of course, yes. Even the beam splitter, if they moves, then the relative length changes. Therefore, it's obvious that the even beam splitter cannot be moved.
Yeah. Sorry. So we don't have to stabilize the beam splitter.
You have to.
Oh, okay.
You have to. Every mirror needs to be stabilized, typically to an accuracy of picometers.
Yes. And so you also use the cryogenic system to cool them down.
Yeah.
Oh, okay. Yes.
Yeah.
It's interesting. Maybe I will read it furthermore.
Yes.
Yes.
Well, in fact, the little movie I showed had only, say, 3 mirrors, but that is too simple. Yes. In fact, we have about 20 or so important mirrors in the system.
Thank you.
Okay, thank you for your presentation. And my name is Kesini. I'm a physics student too, and like physics like that boy. Yes. But sometimes when I do experiment, I stuck with a wrong experiment or wrong result. And like your Nobel Prize, like your before they know that neutrino has mass, before many people think neutrino has no mass. Right? Yes, and why do you do over that? Some people think it's no math.
Okay, thank you. Well, certainly, this point I skipped completely today. But, well, actually, this was essentially by chance. In the Kamiokande experiment, before Super Kamiokande, we wanted to observe proton decays. And the background to the proton decay events are the neutrino interactions. Therefore, we thought we need to understand the neutrino interactions. Then we found that the number of muon neutrinos we observed was much fewer than expected. Then, from that time on, our serious study on neutrinos started. And essentially, after 10 years in Super Kamiokande, we were able to clearly show that neutrinos oscillate. So the whole story began as a kind of fortunate accident.
Okay, thank you.
So when you upgrade from the super Kamiokande to hyper Kamiokande, certainly the size bigger, but I just wondering, is there any new technology installed in the new one?
Oh, yes. Well, certainly, because of the size, we need various new technologies in hyper Kamiokande. For example, if we use the super Kamiokande photodetectors in hyper Kamiokande, it's a disaster. Because, well, these photodetectors needs to have a very high pressure tolerance. But 40 meters and 70 meters are completely different world. So we newly developed the very strong photodetectors. In addition, well, in the old days, Super Kamiokande, we read out the signal at the top of the detector. Well, of course, the cable length was, says, at most 60 meters, but still it was okay. But now we think this is too long. Therefore, we decided to read out whole signal in the water. Then the signal will be digitally transferred to the top of the tank. So there are many, many technological improvements in the detector.
May I ask one question? Actually, about the neutrino, you say that for the first generation, neutrino electron, it's quite hard to predict what is that mass in your table. Could you elaborate a bit why it's hard and how it's come up to the idea?
Yeah, thank you. Well, I didn't tell anything detailed, but neutrino oscillations can only tell the neutrino mass difference, or more exactly, neutrino mass square difference. Anyway, neutrino mass difference. Therefore, it's extremely important, extremely difficult to measure the lightest neutrino mass. As well, we do not have good way. So if you have very good idea, please try.
Then we ask you tips of how to talk to each other and then, try to get funding to build something new. Thanks.
Thanks for the answer. Another question, maybe in physics question. We have many flavor or type of neutrino, maybe 3, right? And the way to observe it, we indirectly observe it by detecting photon. By detecting the photon, right? The light. When we detect neutrino, we detect the light from the process of collision. And then the photon look the same, they indistinguishable. How can we tell that this photon come from this kind of neutrinos?
Type of neutrinos.
Right. How can we interpret?
Thank you. Yes. Well, okay. Of course, an electron interact with a nucleus. An electron neutrino interact with a nucleus. Electron is produced. A muon neutrino interact with the nucleus. Then a muon is produced. Then electrons have a very small mass. Therefore, they are essentially ultra-relativistic. And these ultra-relativistic particles propagating in the water emit photons, high energy photons. Then these high energy photons converted to E plus and E minus. This kind of very complicated phenomena happens. And eventually, a single electron become an electromagnetic shower. And so these many particles contribute to the Cherenkov ring. And on the other hand, muon is a heavy particle, therefore not ultra-relativistic typically. Therefore, they simply go straight, single particle. Therefore, the pattern of the Cherenkov ring is rather simple. So we use the difference of the pattern, event pattern, to recognize the neutrino flavor, neutrino type.
Of detail there. About gravitational wave. How is the occurrence frequencies of the events? Is that like very, very often or very rare? When the gravitational wave detection, how many events per year or per day? Is that very frequency? Like is it happen in daily basis or once a year, few a year?
Thank you. Well, unfortunately, we have not observed gravitational wave events yet. But our, say, design goal is to have the sensitivity up to, say, 140 megaparsec distance for binary neutron star mergers. And if we achieve this sensitivity, I think we would observe events in every maybe 3 days or so.
Okay. So now, do our knowledge and theory or maybe technology is good enough to predict when it's going to happen and when we're going to detect it in like precise time? It's like solar eclipse that in the past we don't know anything about it. We cannot calculate the date, time. But now when we know physics, we know mathematics, that we can tell exactly when it happened in the futures. But now do we have that level yet for gravitational wave events?
Well, most of the gravitational wave events are mergers of the binary black holes. And we have essentially no way to know where is the binary black holes. Therefore, without gravitational waves.
So just passively detect, waiting for it.
Yeah.
Okay. Thank you, sir.
Thank you for your inspiring talk. My name is Krishnutivakan Sasithon. I'm also a lecturer in physics program. You mentioned about in your talk that in early when the universe began to like hot, and you say that matter and antimatter like annihilate, but we know that it's not true. And how's the neutrino tells you about what would happen, why the matter is not unequal, and even though in the cosmological model that you have something else like dark matter or dark energy. Can you tell me about that?
Okay, thank you. Thank you very much for this question. Well, okay, certainly I skipped completely for this part. Well, okay. Now, we found that neutrinos are have a very, very small mass compared with other particles' mass. Then people believe that there should be reason for the very small neutrino mass. And I would say the consensus is there must be neutrino-like particle, but with very heavy mass. And well, I don't go into detail for this point, but because of this very heavy mass, the ordinary neutrino get very small mass. But anyway, now this neutrino-like very heavy particle should have been created in the Big Bang universe. Then these particles, of course, because they are unstable, they should decay immediately. But when they decay, they may have produced the present source of matter excess. There must be some very tiny matter-antimatter imbalance in the decay of these very heavy particles. This is the basic idea. And in order to produce a very small imbalance in the matter-antimatter in the decay, there must be a phenomena called CP violation, that is charge and parity violation, combination of charge and parity violation. And this should be occurring. And well, of course, we cannot directly check with these heavy particles, but this nature is reflected to the neutrino sector. Therefore, we should check the CP violation in the neutrino sector. This is the base for my explanation.
Thank you.
Sir, thank you very much for your inspiring talk. I'm Bunyalit Chatthong. I also physics lecturers. Actually, just 2 weeks ago, I had a chance to listen to high school projects. and they were setting up very simple experiment. They had this kind of circular fabric, and at the center they have two rotating balls, and then they kind of send some kind of two-dimensional waves, and then they measure, and then they try to compare this with gravitational waves. By no means I am no expert in this field, so I gave them some suggestion, but if I would have a chance to go back to them and deliver the expert suggestion, how would you improve their experiment?
Okay, thank you. Well, certainly I would like to see what they are doing.
All right, maybe I have a question for you. It's quite personal. Along the way from started your scientific career until now that you got a Nobel Prize, what do you have to sacrifice in your life? What do you have to lose in your life to get this success along the way? I mean, there is some time that you are not happy about going through this life.
Okay, what I lost. Thank you. Well, certainly, I have to work hard. That is true, I think. And therefore, I didn't have much time to spend with my wife, with my family, and that is a loss.
Hello?
Yeah.
My name is Wasita Bunuan. I'm from Faculty of Law. As young people and as a law student, I want to have some question for you. I appreciate about history behind of supercomputing, and as a young people, I have a question about the International Union of Pure and Applied Physics. It's important of the key of your speech that we have to collaboration together, international cooperation about scientists, but their interest in international relation that we have some war. So without of not being silent, what other way that you want to young generation to do in the future that to do in the practical way to develop this union and make a more peaceful way together in the future? Thank you.
What
young people should do to create the peace?
Yeah, okay. Thank you. Well, well, is it okay to answer to your question as a scientist? Well, certainly, if I'm a politician, my answer will be very different. But anyway, as I discussed, we think in general it is very important to know many people in the world. So, whatever you do in the future, I think I would like to strongly recommend you to have many friends in the world. And that way, I think implicitly you will contribute to the peace building.
Hello.
Hello.
Okay.
I'm so sorry since we have taken quite a lot of time for this
Can I have a question?
session.
Just the last question, please.
Maybe you can ask him in person or after this because we have to proceed to the closing ceremony right now. I'm so sorry.
Okay.
Okay.
Never mind. Thank you.
Okay, now we will now proceed to the closing session. So I would like to invite Assistant Professor Dr. Niwat Kelpadap, Prince of Songkla University President, to give the first token of appreciation to the speaker.
Thank you.
Okay.
Yeah.
And next, I would like to invite Professor Anjana Prathep, the Dean of the Faculty of Science, to give the second token of appreciation to Professor Takaaki Kajita.
This is a laser and this is a pumpkin building. A special ceremony for the 55 years.
Thank you.
Okay.
Thank you.
And may I ask Mr. Uwe Morawetz to take a photo shoot with Professor Anjana and Professor Niwat. May I invite the Vice President and Deans and the Deputy Deans to take a photo shoot with the speaker. And may I invite all the distinguished guests from the front row please take a photo.เดี๋ยวจะมีเซลฟี่กับทุกคนในห้องนะคะ หลังจากช็อตนี้นะคะ Okay, thank you everyone. Now may I ask Professor Takaaki and Dr. Niwat and Professor Anjana and Mr. Uwe to stand on the stair to take the photos with all of the guests of the audience.เดี๋ยวหลังจากช็อตนี้นะคะถ้าแขกคนไหนอยากจะถ่ายรูปนะคะเป็นที่ระลึกกับโปรเฟสเซอร์ก็เชิญได้เลยนะคะมีเวลาประมาณ5 นาทีนะคะเผื่อใครอยากจะเซลฟี่ใครอยากจะถ่ายรูปร่วมกับโปรเฟสเซอร์ทากากิหรือว่าอยากจะคุยเป็นการส่วนตัวนะคะเชิญได้เลยข้างหน้านะคะหลังจากช็อตนี้เนาะเดี๋ยวถ่ายรูปหมู่ก่อนนะคะยิ้มหน่อยค่ะยิ้มหน่อย Smile everyone smile เห็นทุกคนนะคะเห็นทุกคนนะคะ 1 2 3 cheese ขอเฮนะคะขอเฮ 1 2 3เฮ นักเรียนมาเซลฟี่ได้เลยนะคะใครอยากถ่ายรูปกับ Professor เชิญด้านหน้าได้เลยนะคะมาได้เลยค่ะมาได้เลยค่ะใครอยากเซลฟี่ใครอยากถามอะไรนะคะเชิญได้เลยค่ะอาจารย์มีเวลาไม่เป็นไรไม่
เด็กๆลูกแป๊บหนึ่งครับแป๊บหนึ่งอยู่ในความสงบนิดนึงเดี๋ยวเรายังมีเซกชันต่อเนาะนิดนึงยังไม่เสร็จงานนะครับมีแบบประเมินด้วยนะครับในระหว่างนี้เนี่ยถ่ายรูปได้แต่ว่าเดี๋ยวขอทางให้ท่านอาจารย์ด้วยโอเคไหมนะครับโอเคนิดนึงเดี๋ยวให้อาจารย์ลงมาข้างล่างนิดนึงนะครับเพื่อใจเย็นเข้าใจนะครับทุกคนนิดนึงนะครับนิดนึงโอเคเราจะได้ถ่ายกันดีๆนะโอเคเดี๋ยวเชิญทีละเซตนะโอเคครับโอเคเด็กๆที่เหลือนะครับถ้าเป็นไปได้รบกวนนั่งอยู่ในที่ตัวเองก่อนนะครับเพื่อความเป็นระเบียบเรียบร้อยเนาะนะครับนั่งอยู่ที่ตัวเองให้เรียบร้อยก่อนนะครับเดี๋ยวเราจะมีเสวนานิดนึงนะครับเดี๋ยวจะมีเสวนาต่อหลังจากนี้นะครับยังไงอาจจะรบกวนพวกเรานิดนึงเนาะเพื่อไม่ให้เกิดความวุ่นวายมากเกินไปนะครับโอเคเดี๋ยวพอหอมปากหอมคอนะครับเดี๋ยวเราถ่ายรูปพอหอมปากหอมคอนะครับเดี๋ยวเราจะได้ให้อาจารย์เนี่ยได้ไปพักผ่อนด้วยนะครับเดี๋ยวให้อาจารย์ได้ไปพักผ่อนด้วยนะครับโอเคเดี๋ยวขอให้เด็กๆถ่ายเป็นเซตนะถ่ายกันเป็นกลุ่มเลยนะครับเป็นกลุ่มเลยเพราะถ้าถ่ายคนเดียวเดี๋ยววันนี้ไม่เสร็จแน่นอนนะครับเดี๋ยวถ่ายกันเป็นกลุ่มนะเรามีเวลาให้ตรงนี้เซกชันนี้ประมาณ5 นาทีเนาะนะขอเป็นกลุ่มนะขอเป็นกลุ่มมาพวกเราเข้ามาเป็นกลุ่มเลยเด็กๆเข้ามาเป็นกลุ่มเลยนะครับโอเคขอเป็นกลุ่มใครที่ถ่ายเสร็จแล้วกลับไปที่นั่งของตัวเองเลยนะครับใครที่ถ่ายเสร็จแล้วกลับไปที่นั่งตัวเองเลยนะครับโอเคเด็กๆขอเป็นกลุ่มนะขอเป็นกลุ่มนะขอเป็นกลุ่มนะครับเดี๋ยวอาจารย์มีเวลานิดหน่อยนะครับเดี๋ยวอาจารย์จะต้องไปพักผ่อนนะเดี๋ยวให้ท่านโนเบลไปพักผ่อนนะครับโอเคขออีกสักกลุ่มหนึ่งขออีกสักช็อตหนึ่งนะครับขอช็อตเดียวนะครับเดี๋ยวจะให้อาจารย์พักผ่อนแล้วขอช็อตเดียวช็อตสุดท้ายนะช็อตสุดท้าย1ช็อตครับช็อตสุดท้ายช็อตเดียวขออนุญาตนะเด็กๆขออภัยด้วยนะครับขออภัยด้วยพี่ขอ1ช็อตสุดท้ายนะครับเดี๋ยวให้อาจารย์ไปพักผ่อนนะโอเคเดี๋ยวขอให้อาจารย์ไปพักผ่อนนะลูกนะโอเคโอเคได้อีก1ช็อตครับอาจารย์อนุญาตท่านโปรเฟสเซอร์อนุญาตโอเคเร็วพวกเราทำเวลาหน่อยเร็วมาเป็นกลุ่มเลยข้างหลังมวห้องมวเป็นกลุ่มเลยนะลูกนะโอเคเดี๋ยวอาจารย์ได้พักผ่อนนะโอเคอาจารย์อนุญาตอาจารย์อนุญาตกลุ่มนี้เลยกลุ่มนี้มาเลยทั้งกลุ่มแล้วลูกเข้ามาเลยเข้ามาเลยทั้งกลุ่มรวดเร็วทำเวลาหน่อยพวกเราโอเคขอบคุณมากเด็กเดี๋ยวกลับที่นั่งให้เพื่อนๆได้ถ่ายด้วยนะเด็กๆเดี๋ยวกลับที่นั่งนะโอเคเด็กๆระวังอาจารย์ด้วยนะระวังอาจารย์ด้วยโอเคที่เหลือครับใคร ใครที่ถ่ายเรียบร้อยแล้วเดี๋ยวกลับไปที่นั่งของตัวเองก่อนนะครับเดี๋ยวเรามีเสวนากันต่อเพื่อเหมือนเป็นการสรุปนะครับสำหรับกิจกรรมในวันนี้เนาะแล้วก็มีแบบประเมินเพื่อที่จะเด็กๆเนี่ยจะได้รับใบ e-certificate นะครับสำหรับกิจกรรมที่มาร่วมในวันนี้นะครับเด็กๆขอพยายามเป็นกลุ่มลูกเข้าเป็นกลุ่มเนาะเดี๋ยวจะได้ให้ท่านโนเบลอาจารย์ท่านไปพักผ่อนนะครับหลังจากนี้นะครับโอเคโอเคเด็กๆน่าจะพอหอมปากหอมคอเนาะพอหอมปากหอมคอนะครับโอเคเด็กๆทุกคนกลับที่โอเคพอหอมปากหอมคอนะครับโอเค